Well, welcome back to our course on system engineering. This is the second part of the software engineering discussion. And so I'm going to go and continue. We're covering a lot of information. And so in case people wanted to have a little bit of a break, I went ahead and broke this up, and I'll get into now some more of the details. And so now let's talk about the user needs, software requirements, and specifications. And so, as noted earlier, in a software-intensive system, software dominates every aspect and must be an issue at the highest level of system requirements analysis. Thus, the very formulation of the overall system requirements must be subject to analysis and participation by software system engineers. The basic problems in developing system requirements for software-intensive systems are fundamentally the same as all complex systems. However, there are several aspects that are peculiar to the requirements for systems that depend on extensive software automation of critical control functions. One special aspect has been noted previously, namely unreasonable performance expectations based on the extensibility of software. Another is the general diverse customer base with little understanding of what software automation is capable of doing, and hence often not a good source of requirements. The consequences of these and other factors that inhibit the derivation of a reliable set of requirements typically results in a considerable degree of uncertainty and fluidity in software-based system requirements. This is a major reason for the use of prototyping, RAD, or evolutionary development, all of which produce an early version of the system that can be subject to experimentation by users to modify and firm up initial assumptions of desired system characteristics. Several variations of developing software requirements exist today. Of course, many depend on the type of software development model being used. However, some generic features exist regardless of the model chosen. So the figure that we're showing here, it depicts a hierarchy of software requirements, starting with the user needs at the apex. These needs are decomposed into desired features, functions, and performance requirements, and finally specifications. If the system in question is software embedded, the upper levels of the hierarchy are typically performed at the system level, and requirements or specifications are allocated to software system subsystems or components. Well, let's speak to the software generation process. If the system in question is software intensive, the upper level of the hierarchy are needed. In those cases, a separate process for developing and refining requirements may be needed. A generic process presented in this figure shows 4 steps are critical to this effort. And so we'll talk about them one at a time. I'm also just list them over here in terms of just giving you a highlight of that. So the requirements elicitation, the steps seem straightforward, but in reality can be challenging. Bridging the language barriers between users and developers is not simple. Although tools have been developed to facilitate the process, users and developers simply do not speak the same language. Many elicitation methods exist, from direct interaction with stakeholders and users involving interviews and surveys to indirect methods involving observations and data collection. Of course, prototyping can be of valuable use. Then there's requirements analysis and negotiation. A series of methods exist to analyze and refine a set of requirements. These are applicable to software as much as they are to hardware. In general, these techniques involve checking 4 attributes of a requirement set: necessity, consistency, completeness, and feasibility. Once requirements have been refined, they need to be accepted. This is where negotiation begins. Requirements are discussed with stakeholders and refined until agreement is reached. When possible, requirements are prioritized and problematic requirements are resolved. More advanced analysis is then performed, examining the following attributes: business goals conformity, ambiguity, testability, technology requirements, and design implications. Next, we have requirements documentation. Documentation is always the obvious step and can be omitted since everyone is expecting requirements to be documented. We include it because of the criticality in articulating and distributing requirements to the entire development team. Finally, we have the requirements validation. This step can be confusing because many engineers include analysis in the step, and the concept that each requirement is evaluated to be consistent, coherent, unambiguous, etc. However, we have already performed this type of analysis, and the second step above, validation in this context means a final examination of the requirement set in whole to determine whether the set will ultimately meet the needs of the user, customer, parent system. Several methods exist to enable requirements validation: prototyping, modeling, formal review, manual development, and inspection. Even test case development can assist in the validation process. Well, we'll talk about modular partitioning, what we're showing in this figure, in a minute, but let's continue to bring in a few more concepts here. First of all, starting with use cases. A popular tool available to requirements engineers is the use case. Use case has been the best described as a story describing how a set of actors interact with a system under a specific set of circumstances. Because the set of circumstances can be large, even infinite, the number of possible use cases for a system can also be large. It is the job of the requirements engineer, developers, users, and system engineers to limit the number and variety of use cases to those that will influence the development of the system. Use cases represent a powerful tool in bridging the language gap between users or any stakeholders and developers. All can understand sequences of events and actions that need to be performed. Although use cases were developed for describing software system behavior and features, they are regularly used in the systems world to describe any type of system, regardless of the functionality implemented by software. Next, let's talk a little bit about interface requirements. Whatever the type of essential tool of requirements analysis is the identification of external interfaces of the system and the association of each input and output with requirements on its handling within the system. This process not only provides a checklist of relevant requirements, but also a connection between internal functions required to produce external outcomes. In the software-dominated systems, this approach is especially valuable because of the numerous subtle interactions between the system and its environment, which may otherwise be missed in the analysis process. We also have a system architecture in complex systems. It is absolutely necessary to partition them into relatively independent subsystems that may be designed, developed, produced, and tested as separate system building blocks, and similarly to subdivide the subsystems into relatively self-contained components. This approach handles system complexity by segregating groups of mutually interdependent elements and highlights their interfaces. This step is the system engineering method, is referred to as the functional definition or functional analysis and design. In hardware-based system, the partitioning process not only reduces system complexity by subdividing it into manageable elements, but it also serves to collect elements together that correspond to engineering disciplines and industrial product lines. Software-intensive systems, the segregation by discipline is not applicable, while the inherent complexity of software makes it more necessary to partition the system into manageable elements. Software has numerous subdisciplines. And so you can be thinking stuff like algorithms, design, databases, transactional software, which may be in certain cases provide partitioning criteria in systems that are distributed. The characteristics of the connective network can be used to derive the system architecture. So there's this concept of software building blocks. The objective of the partitioning process is to achieve a high degree of modularity. The principles that guide the definition and design of software components are intrinsically similar to those that govern hardware components design, but the essential nature of the implementation results in significant differences in the design process. There is a profusion of standard commercial software packages, especially for business and scientific applications, but rarely for system components. Exceptions to the general situation are the commercial off-the-shelf, sometimes called COTS, software components heavily used in low complexity information systems. Another source of software building blocks is that of the common object. You can call them COs. These are somewhat the equivalent to software to standard hardware parts, such as gears or transformers, or high level to motors or memory chips. They are most often used in the GUI environment. The CO concept is represented by the Microsoft developed Distributed Common Object Model, DCOM. A more vendor independent implementation is the Common Objective Resource Broker Architecture, or COBRA, which is a standard defined by the Object Management Group, OMG, an organization committed to vendor-neutral software standards. However, the CO components comprise only a small fraction of the system design. The result is, despite such efforts as at reuse, the great majority of the new software products are largely unique. Next, we'll talk about modular partitioning, and so that's what we're showing here in the figure. Despite the lack of standard parts, software modules nevertheless can be well structured with an ordered hierarchy of models, modular subdivisions, and well-defined interfaces. The same principles of modularity to minimize the interdependence of functional elements that apply to hardware components are applicable also to computer programming. So the principle of modular partitioning is illustrated in the figure that we're showing. The upper pattern shows the elements of binding, also referred to as cohesion, which measures the mutual relation of items within software modules, represented by boxes with the names or of color. It is desirable for binding to be tight. All closely related items should be grouped together in a single functional area. Conversely, unrelated and or potentially incompatible items should be located in separate areas. Next, we'll talk about architectural modeling, and we're showing an example of a functional flow block diagram that we'll talk about in a minute. Models are an indispensable tool of system engineering for making complex structures and relationships understandable to analysts and designers. This is especially true in software-dominated systems where the abstract nature of the medium can make its form and function virtually incomprehensible. The two main methodologies used to model software systems are called structured analysis and design and object-oriented and design. The former is organized around functional units called procedures and functions. It is based on the hierarchical organization and it uses decomposition to handle complexity. Generally, structured analysis is considered a top-down methodology. The open object-oriented analysis and design, OOAD, is organized around units called objects, which represent entities and encapsulate data with its associated functions. Its roots are in software engineering, and it focuses on information modeling using classes to handle complexity. Generally, OOAD can be considered a bottoms-up methodology. Model-based system engineering is focused on the development of architectural models as the hub of the system engineering effort. SysML supports bottom-up and tops-down modeling analysis. Okay, in terms of structured analysis and design, structural analysis uses four general types of models: the functional flow block diagram, FFBD, the analysis flow diagram, DFD, and the entity relationship diagram, ERD, and there's also the STD. So we're showing an example of a structured analysis diagram right now. So the functional functional flow diagram, the FFBD comes in a variety of forms. We introduce one of those varieties, the functional block diagram, in another chapter. The FFBD is similar, except that rather than depicting functional interfaces like a block diagram, interconnections represent flow of control. Since the FFBD incorporates sequences, sometimes something that neither the FBD nor the IDEF0 formats can do. Logical breakdown points are depicted by summing gates. These constructs enable the depiction of process-oriented concepts. Almost any process can be modeled using an FFBD. And so this figure shows an example of an FFD. So now that we talked about that, that should be a little bit clearer. Next, we'll talk about data flow diagrams. So first, in context, as with a functional block diagram, each function within the hierarchy can be decomposed into subfunctions, and a corresponding diagram can be developed at each level. Functional diagrams are the standard method within structured analysis to depict a system behavior and functionality. So now getting into data flow diagrams, this diagram consists primarily of a set of bubbles, that is circles or ellipse, representing functional units connected by lines annotated with the names of the data flow between the units. Data stores are represented as a pair of parallel lines, and external entities are shown as rectangles. So the figure that we're showing shows a DFD, data flow diagram for the checkout function of a small public library system. Well, we're showing here a robustness diagram, and we'll talk about this more in the next chart. But this is an example of what a robustness diagram can do, and this is trying to illustrate the checkout use case for an automated library system. It is seen to resemble a functional flow diagram, and can be easily understood. A system is normally represented by DFDs at several levels, starting with a context diagram in which there is only one bubble, the system, surrounded by external entity rectangles. Successive levels break down each of the bubbles at the upper level into subsidiary data flows. To system engineers, a software DFD is similar to the functional flow diagram, except for the absence of control flow. Well, let's talk about a few other types of diagrams. There's the entity relationship diagram, ERD. It defines the relationships among the data objects. In its basic form, the entities are shown as rectangles and are connected by lines representing the relationship between them. In addition to the basic ERD notation, the model can be used to represent hierarchical relationships and types of associations among objects. These models are extensively used in database design. There's also the state transition diagram, or STD. And so STD models, what they are used for is to show how the system behaves in responses to external events. And STD shows the different states that the system passes through, the events that causes it to transition from one state to another, and the actions taken to affect the state transition. There's also something called a data dictionary. In addition to the above diagrams, an important modeling tool is an organized collection of the names and characteristics of all data, functions, and control elements used in the system models. This is called the data dictionary and is a necessary ingredient and understanding the meaning of the diagrammatic representation. It's an analogous to hardware parts and interfaces, listing of sets of data and procedure declarations, followed by a definition of the number of procedures that operate on the data. It's not difficult to trace the functional relationships evidenced by functional and procedural calls, and therefore construct a functional call tree, tracing the flow of function throughout the program. So we'll finish up a discussion on the software concept development, analysis, and design. And let's go ahead and talk first about the object-oriented analysis and design, OOAD. So OOAD takes quite a different approach to software architecting. It defines a program entity class, which encapsulates data and functions that operate on them, producing more self-contained, robust, and inherently more reusable program building blocks. Classes also have the property of inheritance to enable, quote, child classes to use all or some of the characteristics of their parent class, with the resultant reduction of redundancy. An object is defined as an instance of a class. The boundary between the steps of analysis and design in object-oriented methodology is not precisely defined by the practitioners, but generally is where the process of understanding and experimentation changes to one of synthesizing the architectural form of the system. This step also involves some experimentation, but its objective is to produce a complete specification of the software required to meet the system requirement. The construction of the system architecture in object-oriented methodology consists of arranging relative classes into groups called subsystems or packages, and defining all of the relationships and responsibilities within and among the groups. Object-oriented methodology has been especially effective in many modern information systems that are largely, quote, transactional. In such programs as inventory management, financial management, airline reservation systems, and many others. The process is largely the manipulation of objects, physical or numerical. Object-oriented methods are not as well suited for primary algorithmic and computational programs. In terms of modeling and functional decomposition, object-oriented design also has the advantage of using a precisely defined and comprehensive modeling language, a unified modeling language, or UML. This provides a powerful tool for all stages of program development. The characteristics of UML are described in another chapter. And so a shortcoming of object-oriented methodology as commonly practiced is that it does not follow a basic systems engineering principle, that of managing complexity by partitioning the system into a hierarchy of loosely coupled subsystems and components. This is accomplished by the system engineering step of functional decomposition and allocation. By focusing on objects, that is things, rather than functions, object-oriented approaches tends to build programs from the bottom up rather than the top down approach inherent in system engineering methods. So object-oriented development does not have a structured element, does have a structured element called the use case, which is basically a functional entity. As described previously, use cases connect the system's external interfaces, often called actors, with internal objects. The application of the use case to design the upper level of the system architecture and introducing objects at lower levels may facilitate the application of system engineering principles to software engineering design. So what are the strengths of UML? The UML language combines the best ideas of the principal methodologies in the field of OOAD. It is the only standardized, well-supported, and widely used software modeling methodology. It therefore serves as a high-level form of communicating software architectural information within and among organizations and individuals engaged in development programs. Moreover, UML has been applied successfully in the software-intensive system projects. Portions of UML are also used to regularly in system engineering to assist in communication concepts and bridging the language gaps between engineers and users, and between software and hardware engineers. A major strength of UML is the existence of commercial tools that support the construction and use of its repertoire of diagrams. In the process, these tools store all the information contained in the diagrams, including names, messages, relationships, attributes, methods, and so on, as well as additional descriptive information. The result is a well-organized database, which is automatically checked for completeness, consistency, and redundancy. In addition, many of the tools have the properties of converting a set of diagrams into C++ and Java source code down to procedural headers. Many also provide a limited degree of reverse engineering, converting source code into one of several top-level UML diagrams. These capabilities can save a great deal of time in the design process. There's also other methodologies. The growing importance of software-dominated systems and their inherent complexities and abstractions has engendered a number of variants of structured and object-oriented methodologies. Two of the most more important ones are discussed below here next. And so we have robustness analysis. This is an extension of object-oriented methodology. It was introduced by Jacobson as a link between object-oriented analysis, which focuses on what, and design, which focuses on how. It classifies objects into three types: boundary objects, which link external objects, actors with the system; entity objects, which embody the principal objects that contain the data and performance services, which are functions; and control objects, which direct the interactions among boundary and entity objects. Robustness analysis creates a robustness diagram for each UML use case, in which the objects involved in the processing of the use case are classified as boundary and entity objects and linked by control objects defined for the purpose. An example of the robustness diagram for a checkout use case was shown in the last slide, so you could back up the recording if you'd like to do that, or see it in the textbook. In the process of preliminary design, the robustness diagram is transformed into class, sequence, and other standard UML diagrams. Control objects may remain as control types, or their functionality may be absorbed into methods of the other objects. To the system engineer, robustness analysis serves as the excellent introduction to object-oriented analysis and design. In terms of functional class decomposition, this methodology refers to as FCD, is a hybrid method that combines structured analysis and object-oriented methodology. It is aimed at the top-down decomposition of complex systems into hierarchy of functional subsystems and components, while at the same time identifying objects associated with each unit. As previously noted, conventional object-oriented methodology tends to design a system from the bottom up and has little guidance on how to group objects into packages. It is said to lead to a flat modular organization. The FCD method seeks to provide a top-down approach to system partitioning by using functional decomposition to define a hierarchical architecture into which objects are integrated. In so doing, it introduces the important systems engineering principles of functional decomposition and allocation into object-oriented software system design. FCD uses an interactive approach to partition successfully lower levels of the system, while at the same time also adding such objects as turn out to be needed for the lower level functions. UML class diagrams are introduced after the first several levels are decomposed. The development of the FCD method have demonstrated the successful use on a number of large system developments. Next, we'll talk about the software engineering development, focusing on coding and unit testing. The process of software engineering development consists of implementing the architectural design of system components developed in the concept development stage into operational software that can control a processor to perform the desired system function. The principal steps in the process and their system engineering context are outlined next, and we'll get a chance to think of them one at a time. First, program structure. Software has been seen to be embodied in units called computer programs, each consisting of a set of instruction. There's the program building blocks. A computer program may be considered to consist of several types of subdivisions or building blocks. As mentioned earlier, in descending order of size, the subdivision of a computer programs and their component names are as follows. One, a module or package consisting of major subdivisions of the overall program, performing one or more programs activities. A medium to large program will typically consist of from several to tens of hundreds of modules. Two, an object-oriented programs, a class is unit composed of a set of attributes, that is data elements, combined with a set of associated methods or services. You can think of them as functions. An object is an instance of a class. Three, a function, say a procedure, is a set of instructions that perform operations on data and controls the processing flow among related functions. The utility or library function is commonly used transform that is supplied within operating system. Or a control structure is a set of instructions that controls the order of which they are executed. The four types of control structures are: one, sequence, a series of instruction; conditional branch, if and if then or else, those types of things. There's loops, do while or do until. There's multiple branches where you can have case statements. Or five, and an instruction is a declarative or executable order to the computer composed of language keys, composed of language keywords, symbols, and names of data and functions. And six, a language keyword, symbol, or name of a data element or function. Finally, a quote data structure is a definition of composite combination of related data elements, such as a record, array, or linked list. As noted previously, software has no commonly occurring building blocks comparable to standard hardware parts and subcomponents such as pumps, motors, digital memory chips, cabinets, and a host of others that simplified designing and building production hardware. With few exceptions, software components are custom designed and built. Well, let's think about common computer languages and the program design language that we're going to be using. A useful method for representing software design produced by conventional structured analysis and design methodology is program design language, PDL, sometimes called structured English. This consists of high-level instructions formatted with control structure like an actual computer programmer, but consist of textual statements rather than programming language, keywords, and phrases. PDL produces a program listing that can be readily understood by any software engineer and can be translated more or less directly into executable source code. In terms of object-oriented design representation, it is easy to see that OOD, or object-oriented design, produces a set of diagrams and descriptive material, including defined objects that constitute intermediate programs building blocks. Through the use of UML support tools, the design information can be automatically converted into the architecture of the program language. Then in terms of program languages, the choice of programming language is one of the major decisions in software design. It depends critically on the type of system. For example, whether software embedded, software intensive, or data intensive computing, whether military or commercial, or whether real-time or interactive. While it is often constrained by the programming talents of the software engineers, the nature of the application should have priority. A language may impact the maintainability, portability, readability, and a variety of other characteristics of the software product. Except for very special applications, computer programs are written in a high-level language where individual instructions typically perform a number of elementary computer operations. And the table that we're showing, it lists a sample of past and current computer languages, their structural constituents, primary usage, and general description. Well, let's continue this conversation and talk about special purpose computer languages. And from the textbook, we have what's called fourth generation and special purposes languages. Fourth generation languages, 4GLs, are typically proprietary languages that provide higher level methods to accomplish a problem solution in a specific domain. These 4GLs are usually coupled with a database system and are related to use of the structured query language, SQL. Sorry. A key feature of 4GL tools is to bring the programming language environment as close to the natural language of the problem domain as possible, and to provide interactive tools to create solutions. For example, the creation of a user input form on a workstation is carried out interactively with the programmer. The programmer enters the labels and identifies allowable entry values and any restrictions, and then the screen becomes part of the application. 4GLs can speed up the development time for specific applications, but are generally not portable across products from different vendors. There are many specialty areas where very efficient high-level languages have been developed. Such languages usually take on the jargon and construct of the area where they are intended to serve. The intent of these special purpose languages is to mimic the problem domain where possible and to decrease development time while increasing reliability. In many cases, the special purpose nature of such languages may limit their performance for the sake of ease of use and development. When undertaking custom software development, the system engineer should explore the availability and utility of languages in a required specialty area. Next, we'll talk about programming support tools, thinking in terms of prototype characteristics as well. To support the effort of developing computer programs to implement software system design, a set of programming support tools and training in their effective use is essential. It is useful for the system engineer and program manager to be knowledgeable about their uses and capabilities. First, there's editors. Editors provide programmers with the means to enter and change source code and documentation. Editors enhance the entry of programming data to specific languages. Some editors can be tailored to help enforce programming style guides. There's debuggers. Debuggers are programs that allow an application to run in a controlled manner for testing and debugging purposes. There are two major types of debuggers, symbolic and numeric. The symbolic debugger allows the user to reference variable names and parameters in the language of the source code. A numeric decoder works at the assembly or machine code level. The computer instructions written in programming language is called source code. To convert the source code produced by the programmers into executed codes, several additional tools are required. So we have compilers. A compiler converts the source language into the intermediate format, also called object code, that is compatible for use in the hardware. In this process, the compiler detects syntax errors, omissions of data declarations, and many other programming errors, and identifies the offending statement. The compiler is specific to the source language and usually to the data processor. Compilers for a given language may not be compatible with each other. It is important to know what standards govern the compiler that will be used and to be aware of any issues associated with code portability. Some compilers come with their own programming development environment that can increase programmer productivity and simplify the program documentation process. Next, there are linkers and loaders. A linker links several object code modules and libraries together to form a cohesive executable program. If there is mixture of language, say C and Java, the combination of the compiler and linker that work on multiple languages is required. Tools that help manage the linkage of complex applications are essential in the management and control of software development. A loader converts linked object code into an executable module that will run in the designated environment. It is often combined with the linker. Then we have software prototyping. So this section of the software system lifecycle describes several modules that use the prototyping approach, either once or recursively. The object of software prototyping is the same as it is with hardware systems when it is used to reduce risk for constructing and testing immature systems or components. In software system, prototyping is generally used even more frequently for 3 reasons. 1, requirements are poorly defined. 2, functionality is unproven. And 3, building the prototype does not require bending metal, only writing code. Conventionally, a prototype is often taken to mean a test module that is to be discarded after its use. In practice, the system prototype often becomes the first step in an evolutionary development process. This strategy has the advantage of preserving the design features of the prototype after they have been improved as a result of user feedback, as a result of building upon the initial programming effort. However, if required, that the prototype program be engineered using a disciplined and well-planned and documented process, this places a limit on how fast the process can be. The choice of strategy must obviously be based on the particular requirements and circumstances of the project. So what we're showing here in this table lists the typical characteristics of exploratory prototypes and are meant to be discarded, and of evolutionary prototypes which are meant to be built upon. The success of a prototype effort is critically dependent on the realism and fidelity of the test environment. If the test setup is not sufficiently realistic and complete, the prototype tests are likely to be inadequate to validate the design approach and sometimes can be actually misleading. The design of the test should receive a comparable degree of expert attention as the prototype design itself. As in hardware systems, this is a key area for system engineering oversight. Well, next we'll talk about software product design, and the figure that we're showing, I'm talking about computer interface models. We'll get to this in a minute, but the figure is showing the most common control modes offered by computer interfaces. There are menu interactions, command languages, and object manipulation. And so a summary of these, some comparative characteristics are given in the table. So for software product design and typical hardware systems development, product design consists of transformation of development prototype hardware components, which might be called breadboards, into reliable, maintainable, and producible units. In this process, the functional performance is preserved, while the physical embodiments may be changed quite radically. Much of this work is carried out by engineers particularly skilled in the problem of production, environmental packaging, materials, and their fabrication methods, and the objective that the final product can be produced effectively and reliably. In the software elements of the system, the product design process is very different. There is no, quote, production process in software, nor is it sensitive to unfavorable environments. However, such aspects of production article are still present. Maintainability is critical due to its more numerous interfaces. Repair by replacement of a failed component, a standby in hardware, does not work in software. Small changes in software must be done carefully because they could affect very large negative effects. And an effective user interface is another critical characteristic of operational software that is often not achieved in the initial version of the system. Thus, considerable effort is usually required to make a working computer program into a software product usable by others. There's no professional group in software engineering comparable to hardware production and packaging engineers. Instead, the process must be incorporated into the software by the same designers responsible for its basic functionality. Such breadth of expertise is often not present in the average software designer, and the result that maintainability of software products is frequently less satisfactory. Okay, in terms of computer user interfaces, as noted previously, a critical part of engineering operational software systems is the design of the user interface. A computer interface should display information in a form giving the user a clear and well-organized picture of the system status, so as effectively to assist the decision process and to provide simple and rapid modes of control. The selection of the appropriate interface mode, display format, interactive logic, and related factors most often require prototype design and testing with representative users. So I mentioned that we have this table that's giving a comparison of computer interface modes. So the most rapidly growing computer interface mode is that of object manipulation. The object being usually referred to as icons. Graphical presentation of information can often present relationships and convey meaning better than text. They enable the user to visualize complex information and form inferences that can lead to faster and more error-free decisions than can be achieved by other methods. GUIs are most commonly seen in personal computers operating systems such as Mac OS and Microsoft Windows. The power of the World Wide Web owns a great deal to its GUI formats. To the system engineer, GUIs offer both opportunities and challenges. The opportunities are in the virtually infinite possibilities of presenting information to the user in a highly enlightening and intuitive form. The challenge comes from the same source, namely the sheer number of choices that tempt the designer to continue to optimize, unrestrained by an inherent limit. Since GUIs involve complex software design, there is a risk of cost and schedule impact if the system engineer is not alert to the hazard. We have advanced modes in designing user interfaces for computer-controlled system. The rapidly advancing technology in the area makes it necessary to consider less conventional modes that offer special advantages. Three examples are noteworthy. First, voice control. Spoken commands processed by speech recognition software provide a form of rapid and easy input that leaves the hands free for other actions. Currently, reliable operation is somewhat limited to careful and enunciated words selected from a fixed vocabulary. Capabilities to understand sentences are gradually being evolved. Two, visual interactions. Computer graphics are being used to aid decision makers by generating displays, modeling the result of possible actions, enabling what-if simulations in real time. Visual interactive simulations is an advanced form of visual interactive modeling. And three, there's virtual reality. It's a form of 3D interface in which the user wears stereo goggles and a headset. Head movement gestures stimulate motions of the image corresponding to where the eye should see in the virtual scene. Such displays are used for a growing variety of tasks, such as design of complex structures and pilot training. They're used in battlefield simulation and games as well. We have unit testing. The engineering design phase of system development begins with the engineering of the individual system components whose function design has been defined and the technical approach validated in the previous phase. Before the resulting engineered component is ready to be integrated with other systems components, its performance and compatibility must be tested to ensure that they comply with the requirements. In software development, this test phase is called unit testing and is focused on each individual software component. Unit tests are generally performed as white box tests, namely those based on the known configuration of the component. Such tests deliberately exercise the critical parts of the design success as complex control structures, external and internal interfaces, timing or synchronization constraints, and so on. Compensating characteristics of software for added testing problems is that the system equipment itself is almost wholly software and can usually be designed and built correspondingly quickly. However, the effort of test design must be as carefully planned and executed as the system design. Unit tests for a given component or major module consist usually of a series of test cases, each designed to test a control path, a data structure, a complex algorithm, a timing constraint, critical interface, or some combination of these. Test cases should be designed to test each function that the unit is required to perform. Since these are typically too many paths to test them all, the selection of test cases requires system engineering judgment. Errors uncovered in unit testing should be documented and decisions made as to when and how they should be corrected. Any corrective changes must be carefully considered before deciding which previous test case should be repeated. Okay, next we have software integration and test. We have a couple of long sections to go, and I think what I'm going to start to do, the lecture is getting pretty long, that I'll do some executive highlights, and you can refer to the textbook for some more details. So the general technique and strategies of system integration applies equally to software components of software embedded systems and to the software-intensive system themselves. This aspect of system development process is critically important, that it must be carefully planned, expertly executed, and vigorously analyzed, and that the magnitude of the effort required is a large fraction of the entire development effort. So there's a lot of things here that we need to be aware of for this to come across well. Well, let's talk about verification and validation. These two terms are not for software only. They apply equally to hardware and systems. They are often used more within a software context than any other. Verification is simply the process of determining whether the software implements the functionality and features correctly and accurately. And validation, in contrast, is the process of determining whether the software satisfies the user's or customer's needs. So in other words, validation determines whether we are implementing the right product. Testing is typically a primary method to perform verification and validation, though not only the only method. So what are the differences in testing software? While the general objective of testing software may be the same as testing hardware, the basic difference between hardware and software, there are a couple things here. Let's think about the couple of things. So first of all, let's think about the test paths. The unconstrained use of control structure may create a multitude of possible logic paths through a relatively small program. This makes it impractical to test all possible paths and forces choices that have to be made. There are interfaces, the typical large number of interfaces between software modules make it difficult to locate strategic test points and to identify the exact sources of discrepancies. We have abstractions. The design descriptions of software are more abstract and less intuitive and understandable than hardware. For changes, the apparent ease of making changes in software requires correspondingly more frequent retesting. For failure modes, the catastrophic nature of many software errors can have some critical consequences. One is the severity of the impact of on the operation. The other is a prompt diagnosing of software. The failure is often frustrating by the interoperability of the system. We have integrated testing. So integrated testing is performed on a partially assembled system as system components are progressively linked together. So this can be helpful and hopefully trying to find issues early. There's regression testing and integration test sense. The addition of each component creates a new interaction among previously integrated components. So we want to be doing this in steps, and so regression can help. There's system tests. This type of testing will evaluate how well the entire system will perform. And so several types of these tests may include recovery testing to see how well the system can gradually or quickly be restored. There can be security testing to evaluate how the system is protected by malicious attempts. There can be stress testing to evaluate how well the logic operates when given abnormal inputs. Performing tests can evaluate the runtime performance. And so those are a variety of things that are out there. Validation tests. These are intended to determine whether or not a system or major subsystem performs the function required to satisfy the operational objectives of the system. Black box testing. We previously talked about white box testing as addressing the known design features of the components. Validation and other system level tests can consider the system under test as a function, as an input to output transfer function without any assumptions of the interface. As such, black box testing is complementary to white box testing and is likely to uncover the interface errors, incorrect functions, initialization errors, and critical performance errors. And finally, we have alpha and beta testing. So software products built for many users, as in the case of much commercial software, most producers have a number of potential customers operating the software before the release. Alpha testing is typically conducted in a control environment. The beta testing is conducted at a customer site without the developer's presence. And so these are ways how you can start to see how well the software is performing gradually before you send it out. Next, we'll briefly talk about software engineering management. And so this deals with some aspects of the management of software-dominated systems that are particularly influenced by the distinguishing character of software, of which system engineers should be cognizant. So there are computer tools for software engineering. Software support tools are software systems that assist in the development and maintenance of software programs, and many major software development efforts. The availability and quality of the support tools may spell the difference between success and failure. So thus we have computer tools for software engineering. We have computer-aided software engineering, or CASE. It is a collection of tools that are designed to standardize as much of the software development process as possible. So this can be a great way to help to streamline things. There's requirements management tools, the derivation, analysis, quantification, revision, tracing, verification, validation, and documentation of operational, functional, performance, and compatibility system requirements have been seen to extend through the system life cycle. For a complex system development is a critical and exacting task that involves operational, contractual, and technical issues. And so this is something that needs to be explored in terms of the management phase. So for software metrics tools, several commercial products and tool sets are available to produce automatically measures of various technical characteristics of computer programs relating to their semantic structure and complexity. There's integrated development support tools. Several tools have become available that provide a set of compatible integrated support functions, and to some cases, the compatibility of importing and exporting data from and to complementary tools for other manufacturers. For example, some use integrated product management, UML diagramming, requirements analysis, and metric acquisition capabilities. Those are some things that are at the resources for software engineering management. We also have software configuration management, and which in system is development is an important, it increases importance with system complexity and criticality. Software systems configuration management is the most critical activity during and after the engineering development stage. And so there's a number of steps that are laid out in the textbook. And then finally, we have the capability maturity model integration. So the abstract nature of software and its lack of inherent limits on functionality, complexity, or size makes software development project considerably more difficult to manage than hardware projects of comparable scope. If you've ever been involved in real life situations, you would have this being something that you would see. So CMMI establishes 6 levels of capability and 5 levels of maturity for an organization. They establish KPIs for each level to provide a basis for assessing an organization's overall systems and software engineering capability. Well, I won't go over the details that the textbook has on these next 2 slides, but just briefly mention them, and you can pause the video and read these. And here is the capability maturity levels. We have a level 0 through level 5, and those establish the qualities for that. And then also for the maturity levels, we have the level 1 through 5 for that. So just finishing up on a few more thoughts before we go to the summary review. So there are system engineering implications, and so we want to be examining what all of this information can reveal. That that would be something that we want to be looking at the KPIs and see what we have. And so what level do we fall in the maturity level and the CMMI level? And then we have metrics. There's a couple types, and you can refer to the textbook for more details. You can be looking and monitoring software metrics. You can be monitoring project metrics. You can be monitoring process metrics. You can be looking at technical metrics. And you can be looking at how best to do the management of metrics. And all those things are laid out. You can also be thinking about process improvement. Is there anything that needs to be adjusted with the programming environment? Does more work need to be done for the integration of case tools? Looking more critically at software components and reuse. All of those are things. Design patterns. Are there different types of reusable design patterns that you could be taking out from what you've done and maybe leverage that in future development? So software systems engineering, we got a chance to get a better sense of what this is all about as a result of what we have talked about here. The textbook also talks about top software engineering issues that have been identified, and you can read through that at the end of the chapter. So let's just go ahead and finish up with the summary review. So the 2 terms system engineering and software system engineering are not synonymous. However, the former refers to the development and delivery of software products, standalone or embedded. The latter refers to the application of principles to the software engineering discipline. We define software as having 3 major components: instructions, also referred to as code, data, structures, and documentation. Coping with complexity and abstraction. The role of software has changed over the past 20 years. Most modern systems are dominated by software. Therefore, software engineering has become a full part of system development. In terms of the nature of software development, software can be categorized as either a system software, A, providing a service to other services, B, embedded software providing functions, services, or features within a larger context, or C, applications software provides services as a standalone system. Systems that utilize software can be categorized in one of 3 ways. A, software embedded systems, which are a hybrid combination of hardware and software. Although predominantly hardware, these systems use software to control the actions of hardware components. Examples are most vehicles, spacecraft, robotics, and military systems. B, there's software-intensive systems, which consist of computers and networks controlled by software. These systems use software to perform virtually all the system functionality, including all automated complex information functionality. Examples are financial management, airline reservations, and inventory control. C, data-intensive computing systems are large-scale computing resources dedicated to executing complex computational tasks. Examples are weather analysis and prediction centers, nuclear effects determination systems, advanced information decryption systems, and other computationally intensive operation. Software has intrinsic differences from hardware, including near infinity variability of software structural units, few commonly occurring software components. Software is assigned most critical functions. Interfaces are more numerous, deeper, and less visible. Software functionality and size have almost no inherent limit. Software is easily changeable. Simple software changes may require extensive testing. Software often fails abruptly without warning signs. Software is abstract and difficult to visualize. In terms of the software development lifecycle models, life cycles of software-dominated systems are generally similar to the system engineering lifecycle described previously in another chapter. While there are plethora of lifecycle models, we can define four basic types: linear, a sequence of steps typical with feedback; two, incremental, a repetition of a sequence of steps to generate incremental capability and functionality until the final increment that incorporates full capability. Three, evolutionary, similar to incremental, except early increments are intended to provide functionality for experimentation, analysis, familiarization, and demonstration. Later increments are influenced heavily from experience with early increments. For agile, the typical steps for software development are combined in various forms to enable rapid yet robust development. For software concept development, analysis, and design, performance requirements for software embedded systems are developed at the system level and should be verified by software developers. Performance requirements for software-intensive systems should be established with close interaction with customers and users and may need to be verified by rapid prototyping. They should not unreasonably stress software extensibility. Software requirements are typically developed using four steps: elicitation from users, customers, and stakeholders, analysis and negotiation with customers, documentation, and validation. True prevailing methodologies for design software systems are structured analysis and design and object-oriented analysis and design. Structured analysis focuses on functional architecture using functional decomposition and defines program modules as a primary structural unit. The methodology proceeds with top-down functional allocation. In contrast, object-oriented analysis and design focuses on classes of objects as program units and encapsulates data variables with operations. This methodology uses an interactive rather than top-down development. Other methodologies include robustness analysis, which focuses on initial object-oriented architectural design, FCD, and combines structured and object-oriented approaches. UML supports all phases of object-oriented development. UML provides 13 types of diagrams presenting different views of the system and is widely used. UML has been adopted as the industry standard. For software engineering development, coding, and unit tests, the engineering design phase of software development implements software architectural design and the computer instruction to execute the prescribed functionality. The phase produces computer programs written in a high-level language and subjects each program unit to a unit test before acceptance. The program language must be suited to the type of software and compiler availability. It must conform with the design methodology and requires that staff experienced with the language be available. Prototyping and interactive development comes in two forms, one purely exploratory and is to be discarded once its purpose is fulfilled, and evolutionary and is to be built upon. In the latter case, high quality must be built in from the beginning. Human-computer interfaces are critical elements in software-intensive systems. These types of interfaces usually use interactive graphic formats and may include voice activation and other advanced techniques. For software integration and testing software systems involves many more test paths and interfaces than hardware and requires special test points for diagnosing failures and their sources. Testing often requires end-to-end system level retesting after eliminating a failure. Alpha and beta testing subject the new system to test by the consumer and expose user problems before wide product distribution. For software engineering management, configuration management for software-dominated systems is critical, and the software in that software is inherently complex and has numerous and deep interfaces. Since software is responsible for controlling some of the most critical system functions, it intends to be subject to frequent changes. CMMI establishes 6 levels of capability and 5 levels of maturity for an organization. The CMI establishes KPIs for each level and provides a basis for assessing an organization's overall systems and software engineering capability. Okay, that's it for this chapter. Thank you very much.